Alright, hello everyone. We're just going to go over a very quick tutorial on neural networks. And, the package we're going to be using is TensorFlow. I'm not going to go over installation and things like that right now. We're just going to go over some of the basics very quickly. We're going to be using a code example from tensorflow.org. And you can access that by going to tensorflow.org, going to learn TensorFlow, tutorials, and quick start for experts. This is just going to let you see the training loop that we're going to be using a lot on this channel, because a lot of the videos will be about training neural networks and the applications that you can use when you start training some neural networks. This is a very simple tutorial. I just went and decided to delete some of the code just to clean it up. They're giving you a full rundown. I'm just giving you a little bit of information. So what you need to do when you want to, do training for a neural network, there's a few things that you need to do. First is you need to acquire the data. Second thing you need to do is you have to acquire a model, whether you load it or you define it, and then you need to train the model on the data. Different workflows, such like typically it's a static data set, but we're going to be going over several reinforcement learning applications, and it's not a static data set in that case because we run the model on the environment to acquire the data and then we train on that data. So let's just go ahead and walk through the code and see what we need to do. So first thing we need to do is we need to import TensorFlow as TF, and from Keras. So we're going to say from tensorflow.keras.layers, we're going to import three types of layers: typical dense layer, which is our multi-layer perceptron; a flattened layer, which just takes any two-dimensional vector or matrix and turns it into a 1D vector; and we have conv2D, which is going to be doing our convolution operations over our 2D images, because this is going to be, I'll say that in a second. And we also need a model to hold our layers. So we're going to say from tensorflow.keras import model. So the intro example for this is we're going to be classifying MNIST digits. So we have digits of the values 0 through 9, and those are given to us as a 2D array. Like a two-dimensional image. And what we have to do is we have corresponding labels for each image of what digit it actually is, and we want to train a neural network to take in the image as input and output the correct class that image belongs to. So to acquire the data, it's super easy. It's just like 2 lines right here, and this is just a helper function put out by TensorFlow for MNIST data. So it splits our x's and our y's, our inputs and our outputs, into train sets and test sets. And for our input, since this is a neural network, we need to do standardization. So we just go ahead, and the pixel values are between 0 and 225. And I'm looking at the shape right now and need to reset. Factories. Time. Okay. So yeah, we get, let's go ahead and run each cell as we go through it. And we're going to look at the shape of our data, which is our X train, our inputs. And so we have 60,000 examples, and it's a 28 by 28 grid. You can look in the documentation, which we're going to be looking at a lot of documentation in several videos, is that our convolutional 2D layer, it has to take inputs as batch size, or two dimensions, because it's a two-dimensional image we're giving, and the number of channels that it has. So currently we have no channels, so we need to go ahead and add our channels, and that's what this does. So you see after, could have probably moved this around a bit more. After we put in this code right here, added channels dimension, we now have a channels dimension in our inputs. So yeah, now we have our rescale data, and we now have our rescale data having a channels dimension as well. You could have used a different way to add a channels dimension. Just make sure that the channels dimension goes last. You could use a separate function, which would have been tf.expanddims, and we could have taken our training set and have, and then it has the corresponding axis where we add our extra dimension. And if we have a value of -1 as our argument for which axis we're going to add the dimension as, it will add it last. So we could have just done this using tf.expanddims with our, xtrain and xtest and -1 as the argument for the axis. And for this example, we're also going to use a data set from TensorFlow, and that's just because as we're doing our so currently all of our data is still in like lists or tuples, and so when we train, we're actually going to train one sample at a time, because that's the way we're going to do it for several of the methods as well in reinforcement learning. But when we want to do our tests, we want to test on a batch, so we're still going to have our test data set as a TensorFlow data set, so we can call it in batches easily without having to do any extra work. So we ran that code. We now know the current shape of our data, and our Y-train, that's just the corresponding label. So now we need to go ahead and define a network. So we imported the model class from TensorFlow. Now we have to go ahead and define a model that inherits from that class. So we can name our model whatever we want. In the example, it's called my model. So it's class my model inherits from model. And we have our initializer function. So in here, what we're going to be doing is we're going to be defining any of our layers that we're going to be using. And well, there's several things that we can define inside of our init class. But we always have to define the layers that are going to be used in the call. So a model, it's just a collection of layers, and as to know the shape and size of each layer, and how to pass information through the separate nodes in the different layers. So we're going to go ahead and don't forget to call super on my model. So we're going to just define a convolutional 2D layer because we're getting an image as input. So we need to let it know, what is it? So it's the size of the image, and I believe this is the number of, not filters, but number of steps, or stride size. No, it's either filters or kernel size, but I just copied this because as you're creating networks, there's going to be a lot of copy and paste. And we need to have an activation function for this convolutional layer, and we're just going to use activation of ReLU. And now we're going to have a super large feature vector, and what we're going to want to do is compress that information into a flat, well, not compress, but we're going to want to reshape it into a flat vector so it can be passed to our dense layers. So we're going to call flatten, and the output from this flatten layer is going to be a one-dimensional array. And then we need to define our two dense layers. So this is going to be one of our deep layers. So it's going to have 128 units and activation of ReLU. And then we're going to have our output layer, which is going to have 10 nodes, and that's one node for each corresponding class label. So we need to also define our call, which is how the information gets passed through the network. So if X is our input, let's say this is a batch size of 1, this is a single image that gets passed in. That image gets passed into our first conv layer, and the output is the output from that first conv layer. And that gets passed to our flatten layer, so now the output from that flatten layer is going to be a single flat vector, and that flat vector gets passed to our deep layer, and whatever the output is going to be for that, and that gets passed finally to our output, and we're going to return that. So when we call our model, we're going to receive the output if we call it on an image. And we can't forget to instantiate our our model so we can go ahead and call it. So, we're just defining our model that we're going to be running our information as by calling a constructor on it. All right, so we're going to go ahead, play that. So one thing that I'm sure you noticed is that we didn't define an input layer in PyTorch. You have to define input layer. In TensorFlow, you can define an input layer, or you could have a model with its inputs unspecified, and it will create all the model weights and variables after you call it on the first data sample. So what we're going to go ahead and do is we're just going to take a couple of our data samples from our training data set, and we're just going to call it on that, so it's going to create our variables for us, and we only need to call it once. So if you see right here, there's no trainable variables, none at all, because although we've defined the model and instantiated it, it doesn't actually know what the input looks like, so it doesn't know how many connections between the input and then the next layer, and then all the subsequent layers. So we're going to go ahead and call it on a single data sample, and we're using tf.expandDims, which is what I said we could use up there. And this is just to create a batch dimension, because for any sample we call, it's going to just be a single image, and TensorFlow by default takes batches of images. So we need to call tf.expandDims. So we're passing in a batch of images, but the batch size is still just one. And then we're going to go ahead and the output is going to be, I'm going to call that preds for predictions, and, whoops, no, sorry. Okay, so, this is going to be our preds. Okay, so we're going to go ahead and call that and see what the predictions look like for a single image. And it's going to take just a second, because the first time that you do it, it's actually creating all of those tf.variables. So you see we actually have the output is a tensor with 10 classes, shape of size, batch size, and number of outputs, which is 10. And the class with the highest value is going to be what it is going to predict having, the most probability of it being that digit. And, if we want to interpret that, we could call softmax on it and see which one has the max value. And, let's say, I don't know, it looks like it's this one. No, this one. This one would be like the highest value. So it'd be 1, 2, 3, 4, 5. Well, it'd be 0, 1, 2, 3, 4, 5. So this would be, the fifth class. So it thinks that this first image is a 5. Okay. But that's what the output is going to look like. And now our model should have trainable variables. So these are the variables that are going to be updated with each pass of, our backpropagation, and then our optimizer step. Our optimizer is going to be stepping on these variables, essentially. So you can see that it has a bunch of variables for each layer. Layer 1, it has all these variables out here, and then it has a bias for that first layer, and then our second layer also, has a bunch of variables and a bias for all those variables, and so on and so forth. So now we know we have our network and the inside is built. So now we need to go ahead and train our network. We have our data set, we have our network. Now let's go ahead and train. And if I didn't say it before, I really don't know much. I'm just, I'm self-taught mostly. So, if I say the wrong things, I do apologize. I'm just trying to help other people out. So the outputs for a network are, the log odds that any one of these classes is the correct class. So we're going to define a loss object for our network for the training. And the training takes a few things. It needs to train a loss with respect to the model parameters. And we do that by taking a step size in the direction of the gradient, because we're doing gradient descent. And let's see. So we have to define our loss object, and that's going to be, we're going to use sparse categorical cross entropy. And the reason we use that is because our Y labels are, they're sparse labels. It's not like we have outputs where it's, one hot encoded for the correct one. This is just labels, 0 through 9. And so those are sparse labels. And the output is, since it's log odds, we're going to say from log its is equal to true, okay? And we need a learning rate. So every time we do backpropagation and, calculate our gradients, the gradients of our loss with respect to our variables, we're going to need to take a step in the direction to minimize that loss. And we need to know what the step size is, or sorry, the optimizer needs to know what that step size is, and that step size is called the learning rate. And right here, since we're going to have batches of size 1, we're going to have a very, very small learning rate because it's going to be a very, very stochastic process since we're doing one sample at a time. So we don't want to take huge steps. And in different applications, we'll say batch size of this or whatever. But for the current example, we're just going to have batch size of 1 for simplicity. And test accuracy. So this is just going to, instead of saying, oh, we're going to be monitoring like the reduction of a loss, we also want to make sure that our accuracy is going up. So with training steps, the more training steps we have, the more accurate we want our network to be in predicting the correct labels. So this is also just predefined by TensorFlow. I'm going to show you a little issue I have with this at the end. But just so you know, our test accuracy and our loss object, these both return scalar values. And whenever we're calculating the loss, we need to calculate, our loss will always be a scalar value with respect to all, the variables that have been watched. So let's go over what a training step is going to do, and let's go ahead and train. So a training step, we just defined this as a function. Well, TensorFlow did, it's a copied example. But the way that a training step will work, and this exists everywhere in training neural network, at least within TensorFlow, is within the scope of tf.gradient tape as tape. And what that does is all those variables that we saw, we need to watch them as we're doing our forward pass, as we're calling our network on our data. So we need to monitor that information, and that gets recorded to our tape. And then when we do backpropagation, it's kind of like, this is like the gist of it, but it's kind of, it's doing the backpropagation with respect to what values have been recorded on the tape. So if we're not recording on the tape, you're not going to get your gradients. I do apologize for saying so many times. Anyways, so we're going to go ahead and for each training step, we're going to get an image, a single image, and we're going to get a single label. And we're going to run our model on our image, and we're going to define training equals true to make sure that we're recording our variables, watching our variables, and the output will be the predictions. So what class it believes we belong to. So our loss object, which is just sparse categorical accuracy, it takes the labels, which is any value 0 through 9, and it takes the predictions, which are the log odds or the log its, and it's going to give us a loss, like how wrong are we, essentially. And then outside of the scope of gradient tape, we say our gradients are equal to tape.gradient, and it's going to calculate the gradient of our loss with respect to our model.trainable variables, okay? And just so you guys are aware, our gradients are going to be the same shape as our model variables. So I don't think I can call .shape on this. Let me see. You cannot. But if this were to give a shape, and we were to call the shape of our gradients, they're the same shape. So then we just tell our optimizer, hey, we want you to take a step. So we're going to say apply our gradients, which is going to take that small little step, and we're going to go ahead and zip our gradients and our model.trainable variables. So they're all taking a step in the correct direction with respect to loss. My goodness. Anywho, so that's all of training. We get our input, we get our output, we make predictions, how different are predictions from the labels, calculate which gives us our loss, find the gradients of the loss with respect to the variables, and apply those gradients to update the variables. So test step is essentially the same thing. We're just returning the metrics, and so we're just going to gloss past that. So, okay, so typically when we're training on a static data set, we might say train for X number of epochs, or we might have an early termination condition, which is saying, if our loss gets below a certain value, stop training, or if our accuracy gets beyond a certain threshold, stop training. And that's what we're going to do. We're going to just say, hey, we're going to have a specific accuracy. If our test accuracy is less than 0.75, we're gonna do our training loop. Otherwise, we're gonna break. We're gonna discontinue the while loop. So so we have our data in xtrain, and we're just gonna iterate through our entire data set and make predictions one at a time. So we're putting each sample into a batch, each output into a batch, and we're calling that our image and our label, and we call a training step on each image and its corresponding label. And then, so this is just, so we update steps, so because we're going to be logging our steps and how many steps it takes to converge, or what we're at a certain point. And we're just going to go ahead, and this is just done so we can get a batch back from our TensorFlow dataset for our test data. So we just get a single batch back, and we're gonna go ahead, and since we're receiving our information as a batch from the dataset, we don't need to add a batch dimension. So we're gonna run a test step, and it's gonna give us our testing loss and our testing accuracy. And we're just gonna go ahead and print our step, what our loss is. I'm gonna just put that as TL, like for test loss. And we're gonna have our test accuracy logged. And we're just gonna do a final break that because we're inside of the while loop. So it will still complete one iteration through the data set if it hits this value. So we're just gonna have it break if it hasn't yet reached that value. So gonna run all these code cells here, just defining functions, and here we're gonna do training. So let's see what it's like for it to train. Okay, and you see our loss is slowly going down, going down, going down. So we are optimizing, and you can see over here that our accuracy started at 0.1, then it's at like 0.15, 0.20, 0.3. And it's a little random, but it's going up to close to 0.35, 0.4, 0.45, 0.5, and if we let this go for, after like 400 steps, we're at like 60% approximately. And if we let this keep going, eventually it's going to stop at 75%. But like one of the issues that I have with this is that you see that these are both scalar values. So technically speaking, if my understanding is correct, in our training step, what we should be able to do is we should be able to exchange this loss object with our test accuracy. Okay, and so right now we're technically increasing our accuracy, but if we wanted to update with respect to the accuracy instead of our loss, we could just say our loss is our accuracy, but then it's going to be forcing our accuracy down. So we have to have negative accuracy. So we have to optimize with respect to negative accuracy. However, whenever we do that, and let's just assume that this has like trained or close to 75% accurate, like you guys at home probably see, like understand exactly what's happening. It's going to take forever. But I'm going to go ahead and run everything is going to be the same, except instead of optimizing with respect to the loss to minimize the loss, what we're actually going to be optimizing is our loss is going to be equivalent to our negative test accuracy, which we want to reduce our negative test accuracy, which will drive our, because we're trying to drive this now closer to -1 instead of our accuracy. We want it to be as close to 1 as possible, like, 0.5 to 0.75 is an improvement. Since we're running gradient descent on this, we want to, we need to make this negative because we need to do minimization. So we need to optimize of our loss with respect to negative test accuracy. So the lower accuracy goes, the closer it's going to get to -1, which will correspond to if we were to remove the negative sign, our test accuracy is going to go up. However, so I just reset runtime and I clicked run all, and you guys will see that the code doesn't run because it doesn't return the gradients. And all of I must say all of my problems that I've ever had with TensorFlow isn't telling me like, hey, like there's no gradients, which is so strange because it's just super minor tweaks that are rationally speaking you're like it's the same thing, like they're both TF tensors, and so it's returning our variables. But if we go to the top, it says no gradients provided for any variable. So if I were to just have this as our loss object, I'm going to go ahead and just print our gradients. I'm going to say print gradients. And I'm going to have break. Okay, well, I'm not going to break actually. So I'm going to have it print gradients, and it's going to continue in a huge loop. Oh, whoops. All right. But you can see our gradients are like I mean, it's not telling us the shape of it, but these are the same shape as our model parameters. However, when I change this to our test accuracy, which is right here, we're going to see that it's going to return no gradients. And loss object. No, yeah, test accuracy. So we're going to go ahead and, stop. And we're going to print our gradients, and it's going to stop on the first one. It's going to say, hey, like, look at our gradients. So we saw that it was the shape. When it is returning the gradients, it's the shape of our model parameters. But when we try to optimize it with respect to something else, it's kind of a problem. So I'll just give it a second. So this is kind of like the style that I intend to be doing. It's not really too structured. It's just going over and it's talking about the code in general. Oh, you saw that? All right, so let's go up. So this is our returned gradients. There's no gradients. So what is this? This would be like our input layer. Sorry, this would be like our this would be like our M, and this would be our B, like our bias. This would be our M, and this would be our B, and this would be our M, and this would be our B. 4 different layers. So this would be like for layer 1. So this would be like for the conv layer, our variables and the bias for it. Our first dense layer are variables and the bias for it. And the bias is part of the variables, but I'm just saying like, the M part, like the slope. And our output layer. But yeah, you can see these clearly are not the same shape. This is not the same shape as this. Why that is happening, I don't know. If anyone could let me know, I would appreciate that very much. I mean, it just makes intuitive sense because I was doing this, and that should be like negative test accuracy if I really wanted to optimize. But yeah, because I was gonna do some tutorials on reinforcement learning, and I thought, hey, like let's just show them exactly what's going on and how we're not like our loss can be anything, and test accuracy would be a great way to like transition, like, oh yeah, like the more rewarding ones are like the ones where it's like more accurate, where you're making the more accurate decisions. So we're going to optimize with respect to making the most accurate decisions, and show how to do that. But I'm unable to do that. And I only tinkered with it for like 20 minutes, 30 minutes. And I was like, it's not worth it. I'll just explain it. I didn't want to just get it running for the sake of it. And I mean, it's pretty useless outside of, an example. But yeah, for reinforcement learning, it's a good thing to note that our negative test accuracy is kind of like very similar to the loss that we had in reinforcement learning, because we're not, the way we determine our loss is different. Anyways, as I do more videos, I'm sure I'm going to get much better spoken and much clearer, and we're going to go over some things like GitHub and putting that stuff on GitHub and adding links and other resources. But it's just going to be a lot of going through documentation and doing code walkthroughs, and maybe clarify confusion for some people. Anyways, like, comment, subscribe. If you didn't like it, let me know why. And hope you all have a very swell day. And yeah, I'll see you guys some other time.